Now what we'd like to do is try to find a formula for the polar arc length element. That is, if we want to compute the arc length of a polar curve, we do the same thing that we would do in Cartesian coordinates. We integrate the arc length element ds between the bounds alpha and beta. This is, of course, in terms of theta. So theta is the independent variable for our polar curves. Alpha and beta, again, are just the boundaries of the ds. But the real big thing here is that we need to find a formula for this that we can actually work with. So this is our goal now, to try to find a formula for the arc length element. And remember, in this scenario, we're assuming we have a polar function. So r is equal to some function rho of theta. And we want to try to find the arc length element of this. We also know that we can parameterize our polar curve in terms of x and y. So the polar parameterization is given by, remember we just plug in this rho into the r of the polar coordinates that we're used to, but the polar parameterization is, this is just equal to f of theta is given by this. X is equal to rho of theta, the radius, which is given by our function, remember, times cosine of theta, and y is given by rho of theta times sine of theta. Okay, so these are just polar coordinates, but where the radius is parameterized by, or as a function of, the angle theta. All right, this helps us because we know a formula for the arc length element in terms of x and y. Our ds as a parametric arc length element is given by x dot squared plus y dot squared, and then times dt, or in this case d theta, because theta is the parameter here. So what we need to do now, we've just reduced this problem to the following one. We know we have this polar parameterization. We're happy with that. What we need to do now is compute x dot squared and y dot squared, add them up. Those will be in terms of theta. Add them up, take their square root, and that will become our arc length element. Okay, so let's go to a new page, but this is what we're going to do now. So we're going to compute x dot, y dot, square them both, add them up, and see what happens. Okay, so remember that our x of theta is rho of theta times cosine of theta. This means that x dot must obey a product rule, because this is now a product of two functions. So the product rule says that this should be rho dot of theta times cosine of theta, plus rho of theta times the derivative of cosine. So this ends up being minus rho of theta times sine of theta. All right, and if we square this, our x dot squared, we have to square term by term. We end up with rho dot squared. I'm going to leave off the of theta, but of course, anytime you see a rho or a rho dot, it's a function of theta. But rho dot squared times cosine squared theta, plus in the middle here, it's going to be negative. So the middle term is going to be minus 2 rho times rho dot cosine theta sine theta. And then the last term is going to be plus rho squared sine squared theta. Okay, so that's our x dot squared. We now need to do the same thing for y and y dot. Our function y was rho of theta times sine of theta. We take the derivative. The dot, remember, means the derivative with respect to theta. So y dot is going to be rho dot of theta times sine of theta. This time the derivative of sine is positive cosine, so this becomes plus rho of theta cosine of theta. And this has to be squared. So it looks very similar to that one, but it is, of course, a little bit different. So y dot squared becomes rho dot squared times sine squared theta plus now 2 rho dot sine times cosine, but we can write it as cosine theta times sine of theta, and then plus rho squared cosine squared theta. Okay, and I've lined this up over here so that now all we have to do, we want to add these two lines up over here. We go term by term, right? So x dot squared plus y dot squared on the left-hand side is going to add up to, and before we get too crazy here, we look at this. These middle terms are the same but opposite sign, so those are gone. Just cancel. And then the first term, we've got rho dot squared, which factors out, and then there's a cosine squared plus sine squared. So this one's rho dot squared times cosine squared theta plus sine squared theta. And finally we look look at this last one over here, it's the same scenario, right? So on this one, a rho squared factors out, and this time it's sine squared plus cosine squared theta. But of course, order doesn't matter when you add. And we're almost done. These two terms, these are just Pythagorean theorem. Those are just equal to 1. And so what we end up with is that our arc length element, in terms of theta, so in our polar parameterization, so for polar functions, our arc length element ds, this is equal to, remember we wrote on the previous page, it's x dot squared plus y dot squared d theta. We could always do exactly what we did, convert it into this polar parameterization and compute it, or what we end up with here, since these are 1, we lose everything but the rows and the row dots. So we end up with the arc length element as being rho dot squared plus rho squared times d theta. And so this is our arc length element. Anytime we want to integrate something and find its arc length, this is what we're going to compute if it's a polar curve. So